In this video, we'll discuss probabilities of compound events. Now, compound events are multi-stage experiments where there are multiple possible outcomes. There are two key words that we will use when we're looking at compound events, the words and the words or. When and is used, all the compound events must occur, and this will mean that the probabilities of the single events will be multiplied together. When the word or is used, some combination of those compound events must occur. This allows the individual probabilities to be added together. One of the great visual representations to help us with understanding these compound events are tree diagrams. So we'll be using those throughout this video to help us understand some of these concepts. So let's first look at the word and being used in probability, and let's say that those events are independent of one another. When this occurs, we can directly multiply their probabilities together. And this would be true whether it's 2 events or 10 events. I can just multiply the individual probabilities together. For example, say that I roll a 3 and I want to land on green on my spinner. These are independent of one another. And I want to know what's the probability that both of those events occur in this experiment. So if I think about that, since they are independent, I can calculate the probability of rolling a 3 on the die and then multiply it by calculating the probability of green. Well, there's a 1/6 chance of rolling a 3 and a 1/3 chance on this spinner of spinning green. That would give me a 1/18th chance of getting both a 3 and landing on green. Now, if we use a tree diagram to help us understand this, we go one step at a time through our experiment. The first thing is rolling the die. When that happens, you could roll the numbers 1 through 6, and they all have an equal chance of occurring. Then, after the die is rolled, the spinner is spun, and there's a chance that on each of those, it could be red, green, or yellow. So I could have 1 red, 1 green, 1 yellow, or 2 red, 2 green, 2 yellow, so on and so forth. And what I'm looking for is where is both 3 and green. And there's only one of those out of these 18 total combinations. Now, once we start dealing with dependence, we have to understand conditional probability. This is where the probability of an event occurs given that another event has already occurred. And the way we write that, you'll see, is the probability of B given A occurred. So let's look at some examples to understand what this means. Say that we're looking at the first 2 cards picked up from a standard deck of cards. And we want to know what's the probability the second card will be an ace if the first card was a jack and there's no replacement. So I take that card, I flip it. I'm assuming that comes out as a jack. That's the first event. When I do that and I lay that jack on the table, that changes the probability because there's now only 51 cards left. So when I'm looking at drawing the ace, I'm now looking at 4 chances out of the 51. So the probability of an ace, given that a jack was chosen, is 4 out of 51. Let's look at another example. Say in this table, we have students that have been surveyed at a local college. And we're looking at the probability that a student owns a cell phone if they don't own a laptop. So we start with the first thing, that if. We're given that they don't own a laptop. So that is that middle column of students, which there are 112 of those students. We don't care about the rest of the situation. We're looking only at this given group of students. Then we're looking at the students that own a cell phone given this specific group. And that would be the 74 students listed here. That means that the probability that a student owns a cell phone given they don't own a laptop is 74 out of the 112. So this comes into play when we have dependent events with the and situations. Say we go back to our cards, where we have 2 cards being selected without replacement. And we want to determine the probability of selecting 2 hearts. What this is going to mean, and if we use our formula up here, that we're going to take the probability that the first card is a heart times the probability that the second card is a heart given that the first one was a heart. So let's look at each of those events. So to select a heart, there would be 13 out of 52 cards. Then we're going to look at selecting a heart given a heart was selected already. Since a heart was already laid out, there's one less heart, so there's only 12 hearts left. And because one card was chosen, there's only 51 total cards now. So when we look at the total probability of these two occurring, it will be the probability of a heart times the probability of a heart given a heart was chosen. So 13 50-seconds times 12 50-seconds. And that will simplify to 156 2,650 seconds, which is 1/17. And our calculators can help us with the simplification as we go along. Now, we've talked about and, we need to also talk about the word or. And or opens up all sorts of possibilities, so you have to be very careful about what the or needs to include or even exclude, because sometimes the or will have overlapping events, where if they're not overlapping, that's technically called mutually exclusive events. But there will be times when we have to take into consideration what's overlapping. So when this happens, we'll calculate each probability and add them together. So let's look at just some examples of the or. Say, rolling a die, what is the probability of rolling greater than 3? So we start with the idea of probability of x is greater than 3. The number we roll is greater than 3. Well, what would create that? Think about all the possibilities on a 6-sided die. That would be rolling a 4, or a 5, or a 6. So we can look at that as the probability of rolling a 4 plus the probability of rolling a 5 plus the probability of rolling a 6. Those three probabilities together tell us what's the total probability of being greater than 3. How about we say what is the probability of the top card of a deck being a face card? So we're looking at the probability of face cards. When we think about, well, what is a face card? A face card is a jack, or queen, or king. So when we think about each of those individual probabilities, we could then add together to give us the total probability of drawing a face card. Now we talked about this idea of inclusion and exclusion. So consider this situation now. What's the probability of rolling a 3, or greater than a 3, or rolling an even number? We got to think about, okay, let's take this one step at a time. We have the probability of being greater than 3 or the probability of being even. So we put a plus here. But what we have to do is we have to remove any situation where it's probability of greater than 3 and being even, because those two situations are not mutually exclusive. It is possible to have on a die a number greater than 3 that is also even. So, well, why do we say this? So let's lay out all the sample spaces. So if I do the probability of being greater than 3, we said that was the probability of 4 plus the probability of 5 plus the probability of 6, because any of those three numbers are greater than 3. The probability of being even is 2, 4, or 6. But look what happens when we do this. The probability of 4 gets counted twice, and the probability of 6 gets counted twice. So what we end up doing is subtracting off those probabilities that get counted twice. So that's what's being removed. Those are the two probabilities that are both greater than 3 and even. We're subtracting that out, and that's why when we look at it, it would be the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 2. So we just have to think about, is there any overlap, and make sure we remove that overlap. So let's go back to our idea of the probability of rolling a 3 or landing a green. So instead of the and, let's look at it from an or perspective. So that would mean that we would look at the probability of rolling a 3 plus the probability of a green, but we need to subtract out any possibilities of 3 and green because of overlap. So let's just lay it out again to help understand what's going on. because this is a two-stage event, I can look at my entire 18 options. So the probability of a 3 actually would be 3 red, 3 green, and 3 yellow. Whereas the probability of being green will be 1 green, 2 green, 3 green, 4 green, 5 green, 6 green. And if you look, there is an overlap. It's the 3 green. That's being used by both groups. So to help with that, we're going to subtract that out. So when we set this up, the probability of rolling a 3 was 1/6. The probability of being green was 1/3. And what we're going to subtract was the and piece, the 1/6 times 1/3. That very unique case, so it doesn't get counted twice. And when we do that, we're going to get a common denominator. So 3/18 plus 6/18 minus 1/18 gives us 8/18 or 4/9. Let's look at one last example here. Say 3 cards are taken off the top of a deck, one at a time. What's the probability that exactly 1 card is red? So when we do this, let's first create a tree diagram to help us. So in the first step, it could be red or black. From each of those, the second card chosen could be red or black. And then from those, the third card chosen could be red or black. And you can see here, there are 8 total combinations, and it continues to grow with every step we add to the experiment. Now the next key part, though, is that because we're taking 1 card off at a time and not replacing it, our second and third cards are going to be dependent upon what happened prior. So when we start, there's 26 red and 26 black cards out of the 52. It's a 50-50 split. Now we have to think about what happens. When I go to a second red, I'm assuming the first one's been taken, which means there's only 25 left out of the 51 cards. Whereas with the black, there's still 26 total black, but there's only 51 cards. Now let's look at the other side of the branch. Say that a black is chosen. Well, if I want to choose a red next, there's 26 possibilities out of the 51, but of the blacks, there's only 25 left out of the 51. So I've got to treat and go one branch at a time as I think of what's going on. So here, if I'm going to go up to my next branch, I've gotten 2 reds already. That means there's only 24 reds left, and there's only 50 cards left because 2 have been pulled out. But there's 26 total blacks still in the hand out of the 50. If I go red, black, red, there's 25 out of 50. And if I go red, black, black, there's 25 out of 50. So I'm just following each branch one at a time to come up with my probabilities. So if I think about going black, red, red, I've now taken out 1 red. There's 25 red left out of the 50. And if I go red or black, red, black, I've got 25 out of 50. Now if I go black, black, red, I haven't chosen any reds yet, so there's 26 left out of the 50. But if I go black, 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 I've already taken out 2 blacks, so there's only 24 left out of the 50 cards. So now we can use this tree diagram to help us put together the situation of exactly 1 card being red. So let's think about what does that mean. That would mean that it either goes red, black, 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 red, black, or black, black, red. There's 3 ways that this could be true, and that's why we have an or between them. And since there's an or between them, I'm going to add their probabilities. And I'm going to follow my tree diagram to create the probability. When it's like this, red, black, black, that means red and black and black. The keyword and. So I'm going to multiply these 3 probabilities to give me that exact piece. So let's go one at a time here. I go red, black, black. That's red, black, black. That's 26 50-seconds times 26 51st times 25 50ths, which is 1300 seconds. Now I'm going to go and follow black, red, black. Black, red to black goes 26 50-seconds times 26 51st times 25 50ths, which is also 1300 seconds. Now I can go black, black, red. So I'm going to follow this bottom path, which goes 26 52nds times 25 51st times 26 50ths, which is 13 100 as well. And because it's an OR, I will add all of those probabilities together, which will end up being 13 34ths. So there's a 13 34ths chance of pulling a red card exactly one time out of these three.